Right. Yeah, thank you so much for having us. So we're Harry and Marti, and yeah, we're just going to present our master's project about the characterization of surface roughness for additive manufacturing using deep learning and X-ray CT. So the main purpose of this project was to basically develop a neural network capable of improving the resolution and the segmentation of images depicting rough surfaces, and that was particularly important within the context of additive manufacturing. And yeah, Harry will explain why that is.
So why do we care about surface roughness, and how is machine learning supposed to help in this? So surface roughness is a critical parameter when it comes to looking at the friction that's generated by a material and its durability and its fatigue lifetime. And how does machine learning help? Well, typically we used to use profilometers to probe the surface. And then, as I'm sure you're all aware, now we use XCT as a non-destructive method, which can actually look inside into the structure of a material. As I'm sure you're aware, there's artifacts that are produced during this scanning using XCT, such as streaking artifacts. We have noise generated by the electronics. And so, yeah, the idea of our machine learning is that we're going to give it these XCT scans, and the machine learning should help minimize some of these artifacts that are generated during the scanning process.
Right. So before we jump into the actual method we use of this project, we're just going to look a little bit into the theory behind XCT and deep learning, which might be a bit obvious for this audience, but can still give a little bit of context. So yeah, basically when we carry out a scan with XCT, what we're measuring is the attenuation of the X-ray within the material, and this arises due to ground swelling and photoelectric effect. And macroscopically, this is described by Bayes' law. So the first one we see on the screen is actually just the outgoing energy after an X-ray beam has gone through material thickness Z and attenuation μA. But this can be expanded for a polychromatic source in order to see how a polychromatic beam would behave. We will not go into details with that, but this is basically important because that's the equation that was being solved in the software we used, and we'll see that in a minute. So basically, when we carry out a CT scan, we just take very many individual radiographs at different angles of the object we want to see. And when we have images at many angles, we go through this process known as reconstruction, which basically back projects the attenuation, so the grayscale value that we found down the line where the photon would have traveled. And obviously, as we see in the images, it doesn't work very well for when we have few projections, but we have a large set of projections at very many angles, then we can get a much clearer image. And obviously this will be in 3D because it's just showing one layer, but there will be very many, so we'll get a three-dimensional image. So jumping onto deep learning, basically deep learning is a subset of AI that is mainly concerned with developing algorithms that can be trained using a set of label data that basically we have some input that we want to match as closely as possible to our ground truth data. And the idea is to basically train the algorithm so that then this can be done for data for which we don't know the ground truth and just get an improved result. So the way a neural network works is we basically have neurons, which are here depicted by the orange circles, which perform a given mathematical operation. For instance, convolution, as we'll explain in a minute. And basically, we put our data through a neuron, it performs a mathematical operation, it gets passed on to the next neuron as a new input, and all the neurons are connected through these weights, which are here represented by the arrows and the W's, and they're basically scalars by which the output gets multiplied by. So when we optimize our algorithm, what is actually happening is that we're optimizing the weight so that the output is as close as possible to the ground truth. And this is done through a process known as stochastic gradient descent, which basically iterates through all the possible weight combinations that can be of use to reduce the difference between the input and the ground truth. So just as an example, convolution, we chose this example because it's actually relevant to this project. So what it actually does is it's very similar to what we understand to convolution mathematics, and we have a large array of data points, which can be just the pixel value of an image, and we slide a small matrix through it known as the kernel, and basically take the dot product of these smaller matrices. And basically this is really useful to detect specific patterns in images, such as gradient differences or horizontal patterns, etc. So this is a very brief introduction. Harry will expand on that a bit later.
Yeah, so as mentioned, to start the machine learning process, we essentially need a huge training data set, and as part of that, we need ground truths. So we wanted to look at rough surfaces, so we used ImageJ and we wrote a macro which essentially generated many cubes with a rough internal surface, like I have here. And yeah, the idea of that was we had very well-defined pixel values all the way along that we could compare our CT scan to, and then slowly train the machine. So there was several different parameters that you could define in this macro. We have kind of the maximum amplitude of the roughness. We have the wavelength, or kind of the distance between changes in the height of the surface, and then also the thickness of the cube. So we were essentially trying to vary as much as we possibly could about these rough surfaces, because in that way we have the best generalization of our model. And thickness was also very crucial, because what you don't want to do is train a machine to work very well on only one thickness of the material when it's looking at the intrinsic properties. So thickness was varied throughout as well.
Yeah, so following the process Harry described, we generated a large data set of basically cubes like this one with different surfaces and thicknesses. So we now do have the ground truth. So the next step was to basically generate the input data, which in this case would be the CT scan of these cubes. So we could have printed them out and put them in a real CT scanner, but obviously that would have been very expensive and slow. So we decided to go for CT scanning simulations. So for these purposes, we used ray tracing software GDXR, which is what I mentioned earlier, that basically solves the polychromatic beam Beers law. And basically, if we tune it to have the right parameters, so we can make it match a real scanner, which in this case we use the in-house X-ray CT scanner at the University of Manchester. And yeah, so all that was left to do was basically take very many scans of these cubes, well, one for each obviously, and we used the core imaging library for a reconstruction step. So one of the issues obviously is that we want to make sure that our simulations are as close as possible to real scans, and the way we qualitatively looked at it was basically we took a profile through the real scan and the virtual scan, basically going through like the side of the cube, so it was shown in the presentation, and we looked at the grayscale value on this side, and we basically see that the behavior, so the behavior of the photons in the simulation is really similar to that in the real scan. We see the coupling artifact, although we see a huge difference that it's basically that of the noise levels. And this is sensible because in our simulations we did not have any electronics noise included, so our simulations are basically a bit too good to be true. However, unfortunately, because of time constraints, we did not manage to add Poisson noise, so to these simulations to try and make them as real as possible. So we just went ahead with this slightly too perfect model. So basically everything in this project should be taken as a proof of concept rather than like an in-depth investigation and development of a very precise algorithm. So this is more of a proof of concept kind of idea. So after this, we basically had our ground truth and our input data, so we could go on to train the neural network, as Harry will explain now.
Yeah, so to quickly give an introduction to the neural network that we trained, this was called UNet, and it was a form of convolutional neural network, meaning that, as Marti explained, there's a kernel which is passed over the image, which is represented by these blue stages. It was a 3x3 kernel. So essentially, we have the image, the initial input image, which is the CT scan, the blurred image with artifacts, etc. On the left-hand side, we have this downsampling stage, where the dimensions of the image are slowly decreased, and that's due to pooling stages, it's called. So essentially here, all the voxel values are put into 2x2 grids, and then even you can do kind of average pooling or maximum pooling, where a 2x2 grid is represented in the next stage by only one pixel. So yeah, during that downsampling stage, you learn, or the machine learns a lot about the larger scale features, the overall shape of the cube. And then we have this upsampling stage on the right, which is where kind of the more smaller scale features are trained, the weights and biases are trained to see these smaller scale features. Other features of the architecture we use are these grey stages, which are called skipped connections. And here, the weights and biases that were trained during downsampling are passed on. And so the information about the larger scale features is maintained within the model, and that's not forgotten during the upsampling stage. And then finally, an important part was the yellow step, which are dropout stages. And here, a very small fraction of the weights and biases that are being learned by the machine are completely randomized and forgotten. And in this way, the idea is that also better generalizes the model. So you're not just training it to understand, only this format of shape. So on to discussing some of our results. First, our investigation centered around whether it was better to use average pooling or maximum pooling stages during our neural network. And we found that average pooling was much better as it represented the surface far more accurately than maximum pooling. So I think this image on the right is probably the most important for our study. And we have, on the left, we have the ground truth, which is one slice of our rough cube. In the middle, we have the GVXR scan. So that's something, we expect the middle column to be somewhat similar to a real CT scan. It has this streaking artifact, and it has blurring and cupping, etc. And then on the right, we have our machine-learned prediction of what the ground truth should look like. And we're very happy with our results in terms of it. It drastically improves the segmentation of the image, and it generally improves the image quality and the resolution far more when the machine is applied to the GVXR scan, which is kind of intuitive because it's training on GVXR scans, so we would expect it to perform very well and when it comes to trying to get back to the ground truth. And then on the left is just an example of how the training went. So the y-axes are both different loss functions that we could use, and you can see this loss is minimized after 3 or 4 epochs or kind of repeats of our training data. And then finally onto the application of our trained model to a real XCT scan. So on the left we have the real XCT scan with streaking, and obviously here there is noise. On the right we have our machine-learned prediction. So while we're happy that the segmentation improves a fair bit, there's clearly work to be done in terms of including noise in the training data. And the streaking perhaps was not adequately represented during our training data as well. As you can see, some streaking on the machine-learned prediction. So I guess kind of a key takeaway of all of this training is that you're only as good as your training data set. And so, there's clear improvements in terms of including the noise in the training data, perhaps using a greater range of orientations, because obviously we wouldn't only want this to work on rough cubes, we would want it to work on anything that you are able to put in a CT scanner. So there's clearly improvements, but we're happy with the proof of concept when the machine is applied to a GVXR scan.
Yeah, so basically to repeat a bit and summarize what Harry just said, we find that the scans for our, the machine learning doesn't work very well on the real scans, but it actually performs really well on the virtual scans. And we concluded that it's because basically we know that we don't have any noise and and our simulations are not perfect. However, if the neural network performs this well on the synthetic data, we believe it could perform equally as well in real data if our synthetic data match better the real data. So basically, our main conclusion is that deep learning could present a really interesting option to improve the resolution and improve the quality of images depicting rough surfaces. So yeah, that's basically our main takeaway. thank you very much for listening. And well, here's a list of references which may be interesting to you or not, but yeah, thank you so much.